Hi class. In this video, we're going to go back and cover a little bit from chapter 1, as well as a section from chapter 3 that are really on the same topic. And the reason that it's appropriate now is that we've seen some methods for um, how to model physical applications in using first order differential equations. And we have seen some methods for theoretically solving those equations. Although we know that we only have ways to solve our equations in some particular, sometimes narrow situations. So we can guess that it's going to come up often that we'll have a physical model of something, we have a differential equation that is maybe too complicated to solve. And so what we really need in practice is an ability to approximate the solutions to our equations. And that's what Euler's method gives us. So let's suppose we have a differential equation, a first order differential equation, dy dx equals f of xy. So remember back from our direction fields where we had our sort of xy plane, and we had some initial points. So let's say here that y at x naught equals y naught. So we're given an initial point, x naught, y naught. And what we're looking for is a solution. So we'll call this function phi of x, and this is the solution that we want. And what we did back in the direction field section, 1.3 or whatever it was, is we knew that our derivative had to equal f of xy. So the derivative of phi, because we can plug phi in for y, has to look like this. And so what we would do is like sort of sketch out these little tangent lines, and we know that our solution would have to sort of follow the direction, right? So I'm just making this up. And so then if we have these direction curves, then and we know that we start off right here, then we can sort of, that gives us something about the shape of our solution. But that was not very formal. It gave us sort of what we used it for was a way to sort of guess at what a solution looked like. But like for this example right here, this is not an obvious shape, and it's not something that we would have been able to guess. But maybe we can formalize this a little bit more and say that if we know this point, we know x naught, y naught, and we know which direction we're going, then maybe we can guess, or maybe we can use that to approximate another point on phi nearby, because we know the direction that it's going. And so that's exactly the solution, or the direction that we're going to take here with Euler's method. So first of all, let's assume the solution exists. If we want to figure out what all the points of phi are, then, well, we have one to start with. So we know phi of x naught equals y naught, because that's our initial condition. We also know that phi prime at x naught is f of x naught, y naught, okay? Because we know that phi satisfies our differential equation. So that comes from our differential equation right there. And so now that tells us something about the tangent line. So let's zoom in on our graph a little bit here. Okay, so we've got our x naught, y naught, and then we have our phi, and we know something about, if we know the derivative of phi, then we can figure out the equation of this tangent line. And the point of a tangent line is that for at least a little while, it's close by to the function that it's tangent to. So let's say this is x1, and we'll dot, dot, dot. So there's a couple points here. I'm going to draw them in different colors, I suppose. And then we can go up here. So the black one is, the y value is phi of x1. And the red one is, I'm going to call it y1. And so y1 is the y1 equals the y value on the tangent line, corresponding to x1. And x1 is just a point near x0. It's just nearby, okay? And the whole point of the tangent line is that we know that these 2 points, y1 and phi of x1, have got to be close together because these two are close. Remember, this is really zoomed in. These two are close, and so the y values have to be close. So y1 is close to phi of x1. And that's the gist. We're trying to approximate the values of phi. Phi is our true solution. We're trying to approximate the values of phi at as many points as we can. And so this is how we're going to approximate it. We're going to say that at least if our x1 and x0 are close to each other, then our y1 is a reasonable way to approximate the values of phi. Okay, so let's try to write that down in equation. So what we're going to do is fix some x values at which we're going to approximate our phi. Because we don't, in practice, remember this is just a practical method. In practice, we don't need to know the value of phi everywhere, because if we're going to be putting it into a computer to do some sort of simulation, then we have to sort of discretize it anyway. So what we're going to do for our approximation is just figure out what it is at some number of points. Okay, so let's let our fix a step size h, some positive value, and it should be small, but since we're just sort of writing it out now, it doesn't matter too much. And then we will take our x values. X is our independent variable. So we will take our evenly spaced points, which we'll call the xn. So xn, we're going to define to be our initial x value plus n steps. So n times h, or n equals 0, 1, 2, etc. So our goal is to compute our corresponding yn, which are going to be approximations to phi at those x values. Okay. So we just talked about how to compute our y1, and that was with the tangent line. So let's write out the tangent line at our point x0, y0. So this is the tangent line at x0, y0. And that's just, y equals mx plus b. So y equals, we're going to call this tangent line t naught, the tangent line at x naught, y naught. So it's some function of x, which we know is equal to, we're defining t naught to be y naught plus x minus x naught times the derivative, which is f at x naught, y naught. Okay, so this is in the form like, x minus, or sorry, y minus y naught equals m x minus x naught, right? And the slope is f at x naught, y naught. And then, of course, I just moved the y naught over. So that's how we got the green equation. So this is the first tangent line. This is the tangent line that we drew up in this graph here, the green line. And as we discussed above, phi at x1, so this is the next point on phi that we want to try to approximate, is approximately equal to y1, which we're going to define right now, as being the y value on the tangent line. So that is equal to t naught at x1. It's the y value on the tangent line corresponding to x1, which is, we can just plug it in, and it's equal to y naught plus h times f of x naught, y naught. And that h comes from this is equal to x1 minus x naught equals, look at the definition of the x's. The 2 points are separated just by an h. Okay, that's exactly how we defined the x's. Okay, so now we've gotten 1 point, but let's do this again. Okay, so repeat. Now what we're going to do, we need to stop using the tangent line, the first tangent line that we drew, because if you look back here, if you get far away, then we have no idea what's going on with y. That distance between the y values is going to get too big. But what we can do is draw the next tangent line. So I guess I'll zoom in a little bit more and draw this out. So our next point is going to be x1, y1. Those are two numbers that we sort of can compute explicitly. And we're going to draw another tangent line that's going to go through here, but we're going to use the slope of the true function phi, because we know that due to the differential equation. So our next tangent line is going to go like this. And so at least we're going to sort of move in the direction that we're going. So we've got our x2, and then we're going to say that phi at x2 is going to be close to what we'll call y2, which is the point on this new tangent line corresponding to our x2. So now we've got to figure out this new tangent line. And that's exactly what we're going to define right now. So the tangent line at x1, y1, we can define like y equals, we'll call this t1 of x, and define this line to be the line that is going through y1 and x1 and has the slope that we calculate at x1, y1. Then we have basically the same thing we saw before. x at, or phi at x2 is the next point we need to calculate, is approximately equal to y2, which we are defining as the y value on t1 corresponding to x1. So it's t1 of x2, which equals y1 plus, now x2 minus x1, these are still h distance apart, and then we have f of x1, y1. And you can see that this is essentially the same thing, right? So if you have the point before, you can calculate the next point. And so we can get this recursive formula where we define xn plus 1 equals xn plus h, and our yn plus 1 equals yn plus h times f of xn, yn for all n. So the only thing that we need to compute this is the f, which we're given by the differential equation, the step size, which we fixed at the beginning, and then we always need, in order to compute x and y of yn plus 1, we need to know what the previous step was. But we know that as long as we knew the first one. So we need to know x naught and y naught, which were given to us at the beginning of the problem because they're initial condition. Okay, so this can be calculated since we know f of xy, what that function is, and we have our first point. Okay, so this is Euler's formula, or Euler's method. It's pretty straightforward. Okay, and this sort of approximation where you approximate the value of something based on its tangent line is really, really, really common. But it's also somewhat, rough and crude, and we can actually talk about how good or bad it is. Okay, so it can be shown that the error of this method is at worst a constant times the step size h. So that means that if you want to have low error, then you need to have low step size. But if you have low step size, that means that you'll have to take a lot of little baby steps, and it will take a lot of computation to get a decent approximation. So the mathematical way to write this is that if you have some approximation y, which is a function of x, but it's also an approximation of your step size h, which is why we have that h in there, but we've written it with a semicolon. Then you say that as h gets smaller, this limit, as h gets smaller, the error between your true value, or your true solution phi, and your approximation, this is the error, oops, however you spell error. Think about if I flipped I said before that the error is at worst a constant times the step size h. And so here's my constant, and if I flipped the h over, that would be constant times h. But I'm writing it this way because it makes more sense in the limit, so that I can put everything as my h gets small. So the limit as my step size h gets small of this whole quantity, this quotient, is going to equal a constant. And so we say this method has order 1. Okay, so Euler's method is an approximation method of order 1. And in general, we can say that a method has order p if where p is the largest integral, where we can put this p down in the numerator. And the way to think about this is that if you have a higher order, if your p is 2 or 3, then when you are when you take your h is a small number. It's always going to be like less than 1. Okay, you don't want it to have to be too small, but it's going to be pretty small. So when you raise it to a power, when you square it or cube it, it's going to get even smaller, right? Like let's say h is 0.1, then when you square it, it will be even smaller. And so if you have a higher order power, then your quantity, then your error is going to get small faster. And that's exactly what we want. And so that's why a higher order approximation method is preferable than Euler's method, which just has order 1. And then the last thing to say, the last kind of notation thing, is that we write that if you have an order p, we write phi at x minus our approximation y at x h is equal to what we say is big O of h to the p. We say that's big O of h to the p. So our Euler's method is order 1, and that's not super great. So we want to try to improve this method, and that's the next thing that we're going to do. So in order to do that, I'm going to derive Euler's method again in a slightly different way. So let's think back to what the problem is that we have. We have our xy axis, and we have some function phi of x that we are trying to approximate. Now let's say that we already know one point on phi. Let's say we have our xn, and then this point here is going to be phi of xn. And so if we want to know another point on here, xn plus 1, where this distance between x's is step size h. So this point up here, that is what we would want to try to figure out, is phi of xn plus 1. So we're again trying to come up with a recursive formula. So assuming that we have some point xn and then the value of the function there, how can we approximate what this next value is going to be? And we know that we can do something with the fundamental theorem of calculus. So fundamental theorem of calculus says that the difference between those two phi values, phi of xn plus 1 minus phi of xn, is equal to the integral from the x values, xn to xn plus 1, of the derivative, phi prime of t dt, right? I mean, think about that. If you if you were trying to solve this integral, you take the antiderivative, which is phi, and then evaluate it between xn plus 1 and xn, and you'd get exactly this, okay? That's why it's the fundamental theorem of calculus. Make this a little bit smaller. And we know what phi prime is, xn plus 1. Phi prime is our function f, evaluated at, so t is our variable, our integrating variable standing in for x. So we have t, and then our y is phi of t dt, okay? So what we're going to try to do, we need to try to approximate this phi value, phi of xn plus 1. And so if we know phi of xn, then we can approximate that difference. And that means that we can try to approximate this integral. But we learned way back at the beginning of second semester calculus a couple different ways that you can approximate the integral. So one way to approximate an integral is with a rectangle. Let's call this integral here I, because I don't want to write it again. I is approximately equal to a rectangle that has height. We can take the height of the rectangle is if you just plug in one of the endpoints into the function. And so we'll take xn because we already know something about xn. So f of xn and then phi of xn times the width of the rectangle is the difference between the 2 points in the limits, which is h, because of the way that we are defining our x values. And so that gives us that our phi of xn plus 1 is approximately equal to our yn plus 1, which we're going to define to be, now I'm going to move this over to the other side. So our phi n plus 1 is going to be approximately equal to, however we approximate phi xn, which if we have an approximation method, then it would be phi n, plus our approximation of our integral, which is h times f of xn yn. Okay, and so this is Euler's method. It's the same thing. And I mean, it makes sense that we get the same thing because this fundamental theorem of calculus is based on the tangent line being the derivative being the slope of the tangent line. All this stuff is related. This is not just two completely random ways of deriving Euler's method. Okay, but the thing is that we're trying to improve Euler's method. And so what can we improve here? Well, we can improve the approximation of this integral. So again, back in calculus, we learned some slightly better ways to approximate an integral than with just a rectangle. And what we're going to use here is the trapezoid method. So that means that our integral I is approximately equal to this formula here, which is the average of if you took the rectangle using the left-hand point or the rectangle using the right-hand point. Because remember, back in calculus, you would use the left-hand rule or the right-hand rule, and sometimes one would be better, and sometimes the other would be better. And so the trapezoid rule splits the difference and takes the average. So now if we replace those phis with y, then you get what's called the trapezoid scheme. Approximation scheme. Looks like our yn plus 1 is equal to yn plus h over 2 so our f at xn yn plus f of xn plus 1 yn plus 1 for n equals 0, 1, 2, etc. So this seems really great, except that what we have here is our yn is defined as the value of f at our yn plus 1. So this is an implicit method. And that means that it's not really obvious how you'd actually solve this in practice. Okay, so what we can do is we want to replace our yn plus 1 with another approximation. And since the only other approximation method we happen to know right now is Euler's method, that's what we'll do. Okay, so what does that give us? We'll say, now we're going to say that our yn plus 1 is defined to be, so write out all the things that we know from the trapezoid method. So yn is fine, h over 2 is fine, f of xn, yn is fine, plus we know our function f, we know xn plus 1. And now instead of yn plus 1, we're going to replace it with, go back to Euler's method. Here we go. Yn plus 1 is equal to yn plus h times f at xn yn. So that's what will come back here, comma, yn plus h times f of xn, comma, yn, close parenthesis, close bracket, for any n. And this is our improved Euler's method. And you might be thinking like, well, why don't we just make whatever approximation? We can just, make these approximations willy-nilly. And the reason that we go and talk about the order here is to sort of make sure that we understand the error that is being introduced every time we make some sort of approximation. And it can be shown that this has, that this improved Euler's method has order 2. So it actually is an improvement over the original one. So that's an introduction to some approximation methods, and we're not going to spend much more time on this in this course because we're not. I like the theory better, but it is important to see, and if you were to do these things in practice, you would also learn how to sort of compute these things in real life. This is what computer science is kind of about, is understanding how you can take this theory and actually compute it and understand the error that is coming from that sort of thing. This is not all of computer science, but it is a really important method to doing numerical analysis. So the homework should be pretty straightforward of just kind of plugging these things in a couple times. And I'm not getting into having you do a bunch of programming, but it is something, if you're interested in, I would strongly suggest a numerical analysis course or studying these things more because it's pretty interesting. And so that's it. Next time we'll move on to chapter 4 and solving second order equations.